Okay, welcome to lecture 13. This lecture is all going to be all about uniform continuity, which is a sort of a arguably kind of a stronger version of continuity, basically. And uniform continuity, it's it's a little bit of a challenging concept, at least partly because it's basically uniform continuity you could describe as a global property of a function, whereas continuity, like we were saying before, is a local property in the sense that the continuity of a function at a point is not determined by whether the function is continuous at like nearby points or any other points. Basically, you can just kind of like focus on a single point, and then the behavior of the function arbitrarily close to that point really is what determines continuity there. Uniform continuity is actually a property we ascribe to a function on an entire set, and it depends on the behavior of the function all across that set kind of at once. So all like simultaneously. The behavior of the function on that entire set determines whether it's uniformly continuous on that set. In a sense, so I guess like informally, f is uniformly continuous if so uniformly continuous on S, let's say. So I'll describe more what I mean by that in a bit, but this is if we can make a choice of basically, okay, if let's say for any epsilon, right? So in the epsilon delta property, right, we're given an epsilon and we're also given x naught, right, which is like a point that we're focusing on to determine whether the function is continuous there. With uniform continuity, it's kind of like we don't know what x naught is, and we're just given epsilon and we have to choose delta. Basically, that's basically what it is. So if for all epsilon greater than 0, we can choose delta independently of x naught, right? In the epsilon delta property, basically. That's basically, roughly what uniform continuity is. Another way of thinking about this is that there's like, there is an upper limit on how much f can vary on S. Okay, so like f is not allowed to experience extremely rapid changes in value, basically, right? Like the value of f cannot change like arbitrarily rapidly between 2 points as those points get closer and closer together in S. That's another way of thinking about it. Of course, these are all very informal and should not be taken too seriously. I'm just trying to give you an intuition for how the idea works. And so it is pretty hard to sort of properly motivate why this is something that we would actually be interested in right now. I think the best thing that the book does to motivate this is, and I'm not sure I'm going to really have time to go through it myself in the lecture, but discussion 19.3, so for motivation. Discussion 19.3 about Riemann sums. Basically, uniform continuity allows us to control the error between upper and lower Riemann sums. So if you remember, when you define an integral, or like, maybe if you've seen some sort of little baby definition of an integral somewhere about, you know, taking Riemann sums where the rectangles have width like 1 over n or something like that. In that situation, well, in those definitions, usually it's just like you just use the value of the function at some point in between, you know, the two endpoints of the interval, and then that becomes the height of the rectangle. But another way of, you know, thinking about it is that you can make kind of a lower approximation of an integral where you take the rectangles to all be below, all the rectangles are like below the graph of f. And then there's also an upper approximation of the integral where all the rectangles are, you know, the tops of the rectangles are above the graph of f. And so the difference between those two approximations of the integral for a given, you know, for a given sort of granularity in the x-axis, the difference between those two approximations is, you know, sort of directly tied to like how much f can like how rapidly f can, you know, oscillate or grow or decay or whatever in the interval that you're integrating over. So if you have the property of uniform continuity, you can use that to control like the maximum change that f can experience, and that kind of controls what the biggest difference between two rectangles could be in the upper and lower Riemann sums. Anyway, I'm not really going to go more into it because it's, you know, we have limited time here, unfortunately. So let me show you examples. So if we look back at the examples we've done so far, so for example, when we showed the epsilon delta property for f of x equals 2x squared plus 1, right? For instance, we chose, we ended up choosing delta less than the minimum of 1 and I believe epsilon over 2 times 2 absolute x naught squared plus 1. Okay, so you can see our choice of delta depends on x naught. So it depends on x naught. Well, it depends on x naught itself, right? So one could ask, like, did we have to make it depend on x naught? So was this necessary? And the answer is actually yes. Okay, if we were at least, if we allow x naught to be an arbitrary real number. Okay, so why is this? Okay, informally, the reason is this, right? If you consider the graph, right? It gets steeper and steeper forever, right? That, you know, if you consider 2 points of like a fixed width away from each other, so if this was like delta and if this was delta, right? Then the difference in the values gets bigger and bigger and bigger forever, right? And you could actually show, so one could show that as x gets large, f of x plus delta minus f of x goes to infinity. At least if we're assuming x is, you know, positive or something, then this will approach. So for like a fixed delta, basically is what I'm saying, right? For a fixed delta, this difference grows arbitrarily large. So it would be hopeless to try to choose a single value of delta that works, that keeps, you know, that keeps f of x within epsilon away from f of x naught for all possible values of x naught, because if x naught gets really, really big, then, you know, if you let x be like delta away from it, the difference in those values is going to get, you know, arbitrarily large. Let's say actually as x naught gets large. That's kind of more appropriate here, I think. So f of x naught plus delta, even just, you know, whatever delta you pick, for larger and larger values of x naught, this difference is going to get huge. So it's not possible to keep it, you know, basically within epsilon, right? So for all values of x naught, that's really the issue here. So that's one example. So this would tell us that f is not uniformly continuous on R. Okay, emphasis on the on R part, okay? Because uniform continuity, again, it's a property that we ascribe to a function on a set, okay? So it's actually true that the given f here is uniformly continuous if you just like restrict your attention to some closed interval, for example. Then it's definitely uniformly continuous because you just kind of have to look near the endpoints of that interval for where the worst, you know, sort of worst behavior of f is, and then pick delta so that f, you know, the change in f is less than epsilon at those places, and then it's going to be true for all the places in that interval that you're looking at that that the change in f will be less than epsilon for the given delta you chose. Regardless of what x naught you're looking at in that interval. So if you restrict your attention to some finite interval, then f actually does become uniformly continuous. But if you're looking at the entirety of the real line at the same time, f is not uniformly continuous because it keeps getting bigger and bigger and bigger, or it keeps growing faster and faster. Really, is the real problem. So there is kind of a relationship between uniform continuity and derivatives, but it's not very precise because there are a lot of continuous functions that just don't even have a derivative, and they can still be uniformly continuous or not uniformly continuous, you know, as the case may be. So it's not directly related to the derivative, but there's sort of like a correlation there, I guess, if you want to think about it that way. Okay, so the book also gives the example of, like, you know, f of x, and I'll try to go through this pretty quickly, but f of x equals 1 over x squared on, they say 0 infinity, but even actually like 0 1, this is not uniformly continuous because, you know, and they draw a very nice picture in the book that I think you should look at. Definitely look at that picture because I think it really, I'm not going to draw the entire thing here, but basically, as you know, if you looked at like x and then like x plus delta, let's say, right, the difference in these values, let's say, you know, f of x minus f of x plus delta, goes to infinity as x goes to 0, okay? Roughly. We haven't even really defined what it means to let x continuously approach 0, you know, to take this limit. We haven't actually defined that. If you want to think about it as like in terms of sequences, like you could say this is true, right? If you take a sequence xn approaching 0 from the right, then this is definitely true. But just heuristically, right? I mean, this, you can kind of understand what I mean, that if you just sort of take this pair of numbers and slide it, you know, slide it over, then the difference here is going to grow to infinity. So whatever delta you pick, there are going to be some places where this difference is bigger than epsilon, basically. Okay. So there won't be a single delta that works for like every x naught. Oh yeah, let's say x naught again. Okay. So there will not be a single delta that works for every x naught in this interval at the same time. Okay. Okay. So with that, let me just state the definition. Yeah, I'm going to just go ahead and state it, and then in the next video, we'll kind of break it down a little bit more and maybe look at some more examples. So the definition is this. So definition. So let f be a real valued function defined on a set S. Okay, and when they say defined on a set, okay, I think the book is kind of being weirdly vague about this. What they really mean is that S is a subset of the domain of F. Okay, so actually, and this is, it causes these really unfortunate, mind-aching, mind-numbing technical issues that I'll try to address in the next video. But allowing S to be a subset of the domain of F is kind of important, but it also causes a lot of weird problems. So that might be why they're being vague about this wording here. Because I feel like this is an intentional choice they made to be kind of vague about it. So I'll sort of, hopefully I'll address that in the next video and it won't just make things more confusing. But basically, yeah, S is just a subset of the domain of F, okay? So then F is uniformly continuous on S if for all epsilon greater than 0, there exists a delta greater than 0 such that for all x, y, and S with x minus y less than delta, we have absolute value of f of x minus absolute or minus f of y is less than epsilon. Okay. So again, remember, you can see in here that like manifestly, you know, our choice of delta can only depend on x epsilon. There's no x naught that was given to us beforehand. We're just given epsilon and the set S basically, right? Epsilon and the set S, and then we have to pick delta, and then any pair of points in S that are within delta away from each other is fair game, right? So if you imagine this as being the game again, you know, the game with the devil, here it's like we agree on the set S beforehand, then the devil tells us epsilon, then we pick delta, and then the devil can pick any 2 points in S that are within delta away from each other, anywhere in S, right? So we have no control over where in S they're going to be. Any 2 points in S, and then the bottom line is that this better be true. F of x minus f of y absolute value better be less than epsilon. Okay. So yeah, I'm gonna call it for this video just to keep the length down. In the next one, I'll try to sort of elaborate on the subtlety of this business with the subset of the domain thing.